Okay, so this is the question I left you at the end of the last class. And some of you have put some answers up, so let's find out if you got it right. I'll guide you through the way I would approach the question. If you've done it slightly differently, that's fine, as long as you're coming out with the right value. Right, so the question asks to calculate the lattice energy of potassium oxide. So the first thing I would do is write out the equation that represents the lattice energy of potassium oxide. So potassium being group 1, oxygen being group 6. When these guys bond in a lattice, you're going to have a formula K2O, because you need 2 plus ions for every 1 or 2 minus ion. Okay, and remember, you're talking about the formation of 1 mole of the lattice. Okay, this is going to be a solid. And remember, we're forming these from their gaseous, scattered gaseous ions. So that's how I'd write out the formula. And then obviously you need to make sure you've got the correct quantities here. So we'll have effectively what would be 2 moles of that going in. And if we sort of break down what we'd have to do, first of all, you're going to have to take your potassium from its standard state, okay? And potassium will exist as a solid, and you're going to have to turn that into its atomized state, okay, which by definition needs to be a gas. And then you're going to need to ionize that as well. So there's there's 2 energy changes we're thinking about here. Okay, now obviously you're actually going to have to do these processes times 2, because we're actually talking about forming 2 ions here. So I could put 2 in front of this, and that'll help me remember that each time I've got an energy value, I'm going to have to double that value. Now I'm just looking at the book, at the data they've given. They said that the enthalpy change of atomization of potassium is 89. That's plus 89. They've said that the enthalpy change of ionization, so the first ionization energy of potassium is 418. So I'll put those values in there because we'll be referring back to them in a moment. Sorry, that's terribly written. Let me erase and tidy that up. It should be 418. Okay, now I'm going to group that together, make it a bit smaller, get it out of the way for now. Okay, let's put that up there because we'll be coming back to it. Now let's think about what we're doing with the oxygen. So for the oxygen, same kind of thing, right? You're going to basically have to first atomize that oxygen from its standard state. Remember, oxygen exists as O2. So then we're going to convert that into O, and then convert that atomized oxygen into its ions. So there we go. But I perhaps should do this slightly differently so you really understand how we're doing this. You're going to have it first becoming a 1 minus ion and then becoming a 2 minus ion. I know perhaps you don't need this extra information, but you need to think of it like this, because otherwise you might miss out on using a particular energy value. Now let's tidy this up a bit. Obviously we've got effectively 2 atoms of oxygen there, so that doesn't really make sense. So we need to have half here. Okay, oxygen in its standard state is a gas. Yes, we want this as a gas. By definition, this should be gaseous. By definition, this should be gaseous as well. By definition, this should be gaseous. And then we've been given the values for these changes, okay, or these energy changes. Looking at the book, this value was plus 249. And then the first electron affinity of oxygen is minus 141. In other words, the energy required to add that electron. And then the second electron affinity is plus 798. Plus 798. So I think the probable area where mistakes would be made here is not considering the fact that you've got to add up both these values here for forming a 1 minus sign and also for forming a 2 minus sign. So watch out for that. I'll group these together and get them out of the way. So we should have all the information we need now up here. Obviously we could do this very quickly when we're used to it, but I'm trying every little step. I think Yasha did say that he found it tricky, so hopefully after watching this it'll be a lot easier. And the final energy change that we're interested in the value for is the enthalpy of formation of this. Okay, and I forgot to write that. Again, according to the data they've given you, that this would be, this delta H of formation is minus 361. Okay, so I've just written out the sum here, and remember, all we are doing is summing all the values together and reversing the signs if the opposite process is happening, okay, or the reverse enthalpy process is happening. Or you can just think of it as reversing the sign of everything that's going on the left-hand side. That's the way I do it anyway. Okay, so 2 times minus 89, remembering that this value was plus 89. Okay, so we've reversed that sign because effectively you're doing the reverse enthalpy process. I've also multiplied it by 2 because we've got effectively 2 moles of this going on. Okay, so it's going to be double the value. And that explains why we've also got the double the value here. As you can see, everything that is on the left-hand side of this equation, the sign has been reversed. And anything that was on the right-hand side, so the enthalpy of formation, the sign has stayed the same. It's as simple as that. You add up all those values and you will get an answer of minus 2281. And I believe that most students came up with that answer, so very well done, okay? Of course, I should put in the units here. This should be kilojoules per mole. Okay, things to watch out for when you get your answer. Remember that lattice energies should be exothermic, okay? So you really need to have a negative value there. If you don't, then recheck your sum.